Welcome to my second extensive playthrough video about Orbit 3 by Joranalogue Audio Design. Orbit 3 is a double-scroll chaos oscillator that contains an electrical circuit that generates chaotic oscillations based on Chua's attractor. If you're curious about what all of this means, I strongly suggest you watch the first video in the series where I explain more about the behavior and history of chaotic systems called strange attractors. The link is in the description. In this video, I'll zoom in a little closer on using Orbit 3 as an audio rate oscillator. I'll briefly explain what the switches, knobs, outputs and inputs do, and show you how the module reacts to different kinds of modulation. After that, I'll break down some patches I made so you can get an idea on how to integrate Orbit 3 into a modular system. For those curious about self-patching Orbit 3, which is really where the power of this module lies when used as audio rates, there's a lot of examples of this in the patch examples. As the bulk of the video are these patch breakdowns, I'll jump straight into taking a closer look at the controls and parameters of Orbit 3, but first I want to thank Joranalogue Audio Design for sponsoring this video. Let's have a look at the front panel of Orbit 3. I have the uppermost switch permanently in the audio position for this video. But if you flip this switch into the low position, you change the speed of the chaotic system into LFO territory. The frequency knob changes the rate or pitch of the oscillator in Orbit 3. It might not seem straightforward to be talking about pitch or frequency when we're listening to an unstable setting with no fixed period. But as you can hear, there's still some kind of pitch, even if the system generates noise. The frequency modulation knob is a polarizer or tenuverter for anything that is connected to the frequency modulation input. In audio mode, this exponential FM input reacts to 1 volt per octave and the polarizer is turned completely to the right. The red cable is a pitch sequence coming from Moskva 2. I patch it into the frequency modulation input and you'll hear that Orbit 3 tracks really nicely. In the center position, the input doesn't affect the pitch of Orbit 3. And when you turn the knob completely to the left, every volt you send in will cause the pitch to go down by 1 octave. You can use this FM input for control voltages coming from sequencers like I'm doing right now, but you can just as well connect another VCO to it to make classic FM sounds. The black cable is a signal coming from the fundamental output from Generate 3. I patch it into the frequency modulation input on Orbit 3. Patch the red cable, which is the pitch sequence coming from Moskva 2, to Generate 3 for a moment. Now when I use the full output of Generate 3 to sync Orbit 3 using the reset input, you can get all kinds of cool timbres. We are only listening to the output of Orbit 3, by the way. Generate 3 is not going into the mixer. tame and wild switch on orbit 3 changes the behavior of the chaotic system. Switching over to the wild setting increases the chaotic nature of the orbits or scrolls, and therefore the chances of the orbits to switch from one equilibrium point to the other. It might be counterintuitive, but I found that by using the wild setting on orbit 3, I found a lot more stable settings that can be used as a VCO. Both settings produce different timbres of noise. This can be really useful for creating different kind of hi-hats or other percussion. I'll demonstrate this in the patch examples. Of course, there's no limit to what you can use noise for, so having a versatile noise generator inside any system is always helpful. The distribution knob changes the width of the scrolls. In practice, this means that the orbits hug the center points more closely, and this results in oscillations that have a smaller amplitude at the start of the cycle and take more oscillations to max out and change over to the other equilibrium point. This knob acts as an offset with a range going from 0 to 5 volts. The distribution modulation knob is a polarizer, and it attenuates any signal that you connect to the distribution modulation input. While this modulation input accepts bipolar signals, the incoming voltage is just added to or subtracted from the offset generated with the distribution knob. Right now I'm sending the fundamental output from Generate 3 into the distribution modulation input. Generate 3 is in low mode. If you turn the distribution up to the left, so 0 volts of offset, and you turn the polarizer for the distribution modulation to the right, any bipolar signal you feed into the distribution modulation input, for example this LFO coming from Generate 3, will only affect the sound when it's in the positive part of its cycle. This is because the negative part of the LFO coming from Generate 3 is subtracted from the offset of the distribution, but the knob is already at 0, so it's at its minimum. And if you turn the distribution knob completely to the right, the LFO coming from Generate 3 will only affect the distribution when it's in its negative part of its oscillation. This is of course because the distribution is already at its maximum, and the positive part of the LFO coming into the distribution modulation input is added to this 5 volts offset. But maximum modulation is already achieved with 5 volts of offset, but adding more voltage to it doesn't really do anything. This might sound really logical, but it's these kind of things that really confuse me when I start using a module and I don't know what to expect. The bottom line is, when you want to influence the distribution in both directions with a bipolar signal, you simply shouldn't turn the distribution up completely to the left or to the right. Of course, you can send audio rate modulation into this distribution modulation input as well. And you can use gates to modulate this parameter as well. The knobs for the two equilibrium points are offsets, and I increase the offset from... A little correction here from the future. The knob for the negative equilibrium point increases the offset from about negative 0.5 volts to a more negative value, but what exactly that value is depends on what output you're listening to. The same logic applies to the knob for the positive equilibrium point. It offsets the value for the positive equilibrium point from about 0.5 volts to a bigger, more positive value. You can modulate these values when you connect the control voltage to the modulation inputs for the equilibrium points. These inputs accept bipolar signals, and whatever you send in is added to or subtracted from the position of the knob, but not in a 1-to-1 ratio, more in a scaled way, because the maximum range of modulation is achieved between 0 and 5 volts, but the actual oscillations of orbit 3 aren't going to be offsetted with plus or minus 5 volts. In practice, turning these knobs to the right increases the offsets of the orbits. Turning them both completely to the right creates the maximum distance between the two offsetted oscillations. Modulating these inputs follows the same logic as a distribution parameter, by which I mean that when the knob, for example for the positive equilibrium point, is at the maximum offset, sending in a positive modulation doesn't have an effect. And of course, you can send in audio rate modulation too. The bottom 6 jacks are the chaos outputs, and we've been listening to one of those the whole time. The signal coming from the positive X, Y and Z outputs is similar, but never the same, and they are 60 degrees out of phase to each other. The signals at the minus X, minus Y and minus Z outputs are just the inverted signals. I've noticed that generally the X output is the brightest and the Z output is the dullest. The EP output, which I have been using to sync my scope, sends out 5 volts whenever the system is orbiting the positive equilibrium point. At low rates, this results in a random or a stable gate. At audio rates, this results in a more digital sounding noise. At stable settings, the signal coming from the EP output is a pulse wave. The reset input on orbit 3 is a cleverly designed circuit that allows resetting the oscillations of orbit 3 by almost any signal you send into it. I find the reset input, together with self-patching, to be the secret weapon of Orbit 3, as it makes almost any setting work in a musical context. Let me patch in a sine wave from Generate 3 to hear what it sounds like. And right now we're still listening to the EP output on Orbit 3. Let's listen to the X output on Orbit 3. It's still being synced by a sine wave coming from Generate 3. And sometimes you get hard sync tones, sometimes it's more of a soft sync. This is rather ambiguous, as it really depends on the behavior of the chaos inside Orbit 3. Like I said just a moment ago, Orbit 3 really benefits from self-patching. By sending different outputs back into the modulation inputs, you can create all kinds of different waves. And for example, it's really easy to create a saw wave by using the -X output into the reset input. Let me adjust the scope. And by trying different outputs into different inputs, you get different kinds of shapes. And then when you start modulating the other parameters, you can get all kinds of crazy effects. Let me patch in a looping envelope coming from maths into the modulation input for the negative equilibrium point. Let me patch the pitch sequence back into the frequency modulation input on Orbit 3 as well. Alternatively, let's try the sine coming from Generate 3. So as you can see and hear, Orbit 3 isn't just a noise machine. With a little help and experimentation, it can create beauty and stability out of chaos. You can make noise if you want, but you can just as well use it as a sine, saw or pulse wave VCO to make melodies, drones, or to modulate other VCOs. In the patch examples, which are coming up next, I'll try to demonstrate some ways I've used Orbit 3 in the context of a modular system. Some patches are rather noisy, others are more musical and clean. The effects I'm using in these patches are an Erica Synths Pico DSP, a Music Thing modular spring reverb, and a WMD SSF TPLR stereo delay. Everything is patched into the Cosmotronics Cosmix mixer and is routed through an IntelliJ U-jack before going into the sound card of my computer. I'm always intrigued by alarms, countdowns, machine noises and general sound design in science fiction movies. The beacon of Icarus 1 in the movie Sunshine is one of those sounds that just blow me away. I like to think that this patch would feel right at home in a science fiction movie. I've connected the -Y output on orbit 3 to the reset input. The -Z output is going into the modulation input for the negative equilibrium point. Turning the offset knob for this equilibrium point gives us all kinds of timbres, different pitches, saw waves, synced sine waves. And when you turn this knob too far to the left, it causes the sound coming from the X output to fade out in a very peculiar way. By sending the -Z output through mats and mixing the signal with a looping envelope, I can automate this offset so I don't need to turn the knob manually. You could just as well achieve this by mixing the -Z signal and a looping envelope in a DC-coupled mixer. I'm clocking a sequencer with the end of cycle gate from my envelope, and this pitch information is connected to the exponential FM input on orbit 3. This gives the sound a little more personality. I've connected two more outputs of orbit 3 to a spring reverb and a delay to add some atmosphere. You might wonder if Orbit 3 is capable of producing a powerful bass sound. In this patch, I've mixed the EP output, which is going through the scope, with the Y output in my MA35 filter, which receives an envelope from Mats for the filter modulation and an envelope from Dual ADSR for the VCA. Orbit 3 is being sequenced by Mosquad 2. Kick and hi-hats are samples from the Pico drums, and Generate 3 is self-patched to make some noise for the snare sound. In this patch, I have the Y output of Orbit 3 self-patched into the reset input. At some settings, this produces a stable, saw-like wave. At other settings, this produces noise or a synced sine. I'm sending in a pitch sequence from Mosquad 2, and the gate is going through Mats into the positive EP input on Orbit 3. And you'll see and hear that by attenuating this gated signal, modulating the positive equilibrium point, you can get all kinds of effects. Sometimes there's a pitch change, sometimes the timbre changes completely. And I think the amount of delay that I added is fitting for this sequence. For this patch, I was wondering what would happen when I found a stable setting on orbit 3 and then modulated every parameter with some kind of control voltage or envelope. So I found a stable setting, and now I will add modulation coming from mimetic digitalis to the distribution and both of the equilibrium point modulation inputs. I'll mute orbit 3 for a moment. Let's have a listen to what Generate 3 is doing. To create this sound, I'm sending control voltages into several inputs on Generate 3. I will now connect the -X output of orbit 3 into the flip input on Generate 3. Now let's listen to both of them at the same time. Additionally, I'm sending a gate into the frequency modulation input on orbit 3. Let's listen to orbit 3 alone for a moment, and then I'll add the signal of Generate 3 again. In this patch, we're listening to the X output again, is going through the scope. I thought it would be interesting to try and listen what it sounds like when I patch the EP output into the frequency modulation input. The resulting signal coming from the X output is relatively stable at these settings. So why not patch the -X output into the distribution modulation input to make it a little less stable? And because we used the frequency modulation input to self-patch orbit 3, unless you own a precision adder, it's no longer possible to send in pitch information to this input. Of course, I can still get orbit 3 to play a sequence by just syncing it to another VCO, in this case Generate 3. And this again gives us all kinds of different timbres coming from the X output on orbit 3. I thought this patch would benefit from a little bit of vibrato, so I patched the output of my frequency central wave runner LFO into the exponential FM input on Generate 3. And now, with a touch of reverb and a lot of stereo delay, this is how it sounds. this example, I'm using Orbit 3 as a noise source for the hats. I'm using the Y output straight into a VCA, which is being controlled by an envelope coming from Mats. And by changing the settings on Orbit 3, you can change the flavor of the hi-hats. In this patch, I'm sending different outputs from Orbit 3 to different filters. The -X and -Y outputs are going to a pair of ripples panned left and right on the mixer. The EP output, which is kind of a square wave, is going to the MA35. The Z output is going into the Bastel Instruments Cinnamon filter, and the bandpass output is going into the mixer. Orbit 3 is receiving a pitch sequence from Moskwa 2, and all the filters are being modulated by a pair of LFOs and an envelope coming from Mats. Watch and listen how this patch evolves when I patch the different outputs of Generate 3 into the reset input on Orbit 3. Later on, I patch the output of Generate 3 into the MA35 filter as well. In this patch, the Z output of orbit 3 is connected to the phase modulation input of Generate 3. Generate 3 is doing the bass, which you'll hear in a bit. Generate 3 is being filtered by the MA35, and the EP output of orbit 3 is connected to the second input of this filter. The X output of orbit 3 is going into the VCA, and it provides the noise for the hi-hats. You can't hear them very well, but they're in there somewhere. The FM patch is coming from braids, is going into a lot of reverb and a stereo delay. In this patch, I'm sending the inverted chaos output and the EP output to a dub-first sequential switch. Pamela is triggering this switch every beat. The yellow cable is a pitch sequence coming from a Matic Digitalis. Instead of using the pitch sequence to send into the frequency input, let's ditch the pitch sequence altogether. The black cable is the output of the sequential switch going into the mixer, but melted with a stackable, so we can use it to self-patch orbit 3. Let's try all the inputs and see what it does. Later on, I'll add the pitch sequence again, but for now, I'm going to enjoy some self-patching. I'll wrap up the video here. I hope you learned something about Orbit 3, the new double scroll chaos oscillator by Joranalogue Audio Design. I'm working on a third video focusing on the LFO or low mode of Orbit 3 as we speak. This video will be released soon. If there's any questions, please leave them in the comments. I'll try to address them in a later video. Thanks for watching.